Thank you very much. I thank the organizers for inviting me. I expect this talk will not be too different from, well, it will be, but not too far away from the audience. It is related to Shaugata's talk in the sense that it's also related with P and NP. But instead of complicated sheaves, what I want to introduce is simple numerical analysis. So I will divide the talk in two parts. First part is a background, and the second part is the theory itself. So let me begin with the background. One good starting point is a paper published by Lenore, Mike, and Steve in 1989. That was a theory of computation and complexity over the real numbers. Okay? Two basic things that were introduced on that paper were the class P over the reals and the class NP over the reals that essentially were meant to capture the notion of problems that are efficiently solvable over the reals, and NP problems that we believe they are not efficiently solvable over the reals, but we don't have a proof right now. Now, the last section of that paper contains some open problems and open questions, and the last question in this last section said the following: finally, to bring machines over the reals closer to the subject of numerical analysis, it would be useful to incorporate round-off error, condition numbers, and approximate solutions into our development. So this is what I attempt to do. So let me remind you a little bit what do we understand by floating point computations. Essentially, computers, when they work with the numbers that have this form. So they have t bits, so zeros and ones. I work in base 2. And then this is a mantissa, and then here comes 2 to the e, where e is an exponent that is in absolute value bounded by a certain value e max. So the real numbers that are somehow represented in this way fall into these two intervals, union 0, and we call these two intervals, union 0s, the range of this number system. Okay? There is some quantity called the unit roundoff, or the epsilon machine sometimes, that is 2 to the minus t, this t here. There is a rounding function that any number in the range of the system is rounded into a number in the system, so that when I round x, what I obtain is x times 1 plus delta for some delta that has absolute value at most the epsilon machine, the unit roundoff. Okay? Once I have that, I can define some sort of floating point arithmetic, because to any of the 4 arithmetic operations, I can replace it by a triddle operation, a floating point operation, such that I operate two, let's say, numbers, floating point numbers if you want. And what I do is I do the true operation, and then I round again. So if I have, let's say, 2 numbers that have each of them 20 bits, I multiply them, I obtain a number that has 40 bits, and then I chop the last 20, and I am 20 bits again. Okay? Sometimes there is, in most theoretical analysis, there is this hypothesis, hidden hypothesis of unrestricted exponents. So really, we assume that this Emax equals infinity. And this is related with overflow and underflow, which are sort of rare phenomena. Okay? So, stability and conditions. We want to analyze how errors accumulate in an algorithm, in a computation, and this depends on essentially 2 things. First, how sensitive is the result of the computed function to perturbation of the data D? And then the answer to this is the condition for this problem and this data. Okay? It depends on the problem and the data. And then we have just seen one example in what Peter explained to us a few minutes ago. Okay? The second is how badly does the algorithm at hand accumulate errors? Okay? And then there is this stability analysis that depends mostly on the algorithm at hand. So this will depend on the algorithm at hand and the dimension of the data. Okay? So let me give you one example so take linear equation solving. I am giving A and B, and I want to compute X, which is A inverse times B. So assume unrestricted exponents, then in that case the condition number of this data, which depends only on A, but such is life, is called kappa of A, and this is the norm of A times the norm of A inverse, and the typical result for a specific algorithm, in this case householder QR decomposition, says that the solution X twiddle that we compute satisfies, for some constant C, that this relative error is bounded by Cn cubed epsilon machine condition number of A times plus a factor that is negligible. So you see here there is the condition number that depends on my data, and then this is essentially, if I start with this precision, this is the Cn cube is what will depend on our algorithm, in this case our QR decomposition. An important remark. That I think the first example I have is that Hestenes and Stiefel showed that very, very shortly after this condition number was introduced, that was introduced by Turing and von Neumann, by the way, plays a role also in complexity analysis. So for many, many algorithms, the number of iterations that we need to do depends on how well conditioned is my data. Okay, and this is key to keep it in mind. Now, what is condition exactly? Well, it's difficult to define because different problems will carry on different definitions of conditions. So for instance, take a decisional problem, a problem that the answer is either yes or no. If I take a data D that is on the yes side, small variations or perturbations of D will produce no change in the answer. So it really doesn't make sense to talk about condition in this way for decisional problems. What we somehow observe is that the distance to the boundary between yes and no plays a role in understanding how fast my algorithm works, or how much precision do I need to find a correct answer. So keep in mind, let's say that condition numbers are defined ad hoc. Now let's go for the theory. Decision problems. First, we need to define which sort of problems we will deal with, and we will just consider decision problems. One important thing for decision problems is that data has two sort of components, right? Discrete and continuous. Okay, you are given a polynomial, and then the degrees of the monomials will be discrete data, but the coefficients of the polynomial is continuous data. So you will somehow have to use both sort of data. Okay. For me, a decision problem is a pair A mu, where A is a subset of the data. I identify with the yes side. And mu is any function from I into 1 infinity. And I call mu the condition number. Okay? I denote by sigma the set ux such that mu u or x equals infinity. And we say that elements in sigma are ill-posed. In general, this sigma will contain this boundary. This boundary needs to be ill-posed because arbitrarily small perturbations will change my answer. So I cannot hope to solve with finite precision the problem at those points on the boundary. Now, one important thing here. Different condition numbers for the same subset A define different decision problems. Okay? This is akin to the situation in classical, that is both discrete and infinite precision VSS complexity theory, where different encodings for the intended input define, and sometimes radically, different problems. Okay, think on, let's say, does a polynomial have a zero? Well, yes, this is a problem that is well defined, but this, from a complexity point of view, is not the same whether the polynomial is given in dense representation or as a straight line program, right?
This disjoint union is over I integers, or because in infinity I don't understand.
What?
What does it take the disjoint union?
This is disjoint union of R infinity, disjoint union of
over I integers.
Integers. So these are vectors of real numbers and vectors of bits. So your data is given as a finite number of bits and a finite number of real numbers. Okay? which is what you need for whatever, describing polynomials, weighted graphs. So the data we consider is the data in the previous transparency. What about machines? Well, a finite precision BSS machine is a BSS machine performing finite precision computations. That's very simple definition. We only need to say what are finite precision computations. So we fix a number, U machine, between 0 and 1, the unit roundoff. And then in a U computation, I simply perform the computation, and at every step of the computation, I replace any number z that I am obtaining in the computation by some floating of z, which is defined in this way. But this is for some delta, so it can be anything. I am not taking any specific rounding function. Can be anything, as long as it satisfies this equality. Okay, so I will define this. It's very useful to have this K-match, which is the log of 1 divided U machine, because this K-match is the precision of the machine. It is, when we talk about infinite precision, is when this K-match is infinite. Okay?
You're not allowed to change this precision during the course of a computation, are you?
Let me make it simple. No. I mean, the question is, if you go at the paper, the answer is yes. There is a class in which you can change, but I won't mention it here. Now, what is complexity? Complexity is dependence of cost on size. Okay? So I need to define size and cost. Let me begin with size. I have a number of reals and a number of bits. So what is the length of this data? The length is how many bits plus how many reals, S plus n. Okay, and what is the size? The size is the length plus the log of the condition number. So the length is something I know a priori, and it's essentially, you know, how many bits and reals and floating point numbers I need to represent my my data. But I need to add here the log of the condition number, which tells me something about the quality of my data, in a way. So, very important, if Ux is ill-posed, then the size is infinity, and otherwise, the size is a natural number. Okay, this is size. What about cost? There will be two notions of cost, which are somehow natural. The number of steps performed before halting, this is the arithmetic cost. How many arithmetic operations have I performed? But then it comes a second cost, which is more delicate, which is the accuracy cost, which is the smallest value of K-match that guarantees a correct answer. Okay? So I perform an algorithm. If my precision is too coarse, so I am near the boundary. If my precision begins rounding off this data and sending it to the other side, even if everything I do afterwards is correct, I will give the wrong answer. But if my precision is very, very fine, no matter what it happens, maybe my algorithm will give me good answer. Okay? So the smallest value of K-match guaranteeing a good answer is the accuracy cost of this algorithm for this input. This is close to the cost in practice.
But this depends on the input?
Yeah, it's the cost of, depends on the input, of course, yeah, sure. So when you're giving an input, the arithmetic cost, you can count it, how many operations will be, and the accuracy cost, you cannot count it, but you can define it. I mean, it's there, okay? And you may compute it. So, clocked computations. I take two functions, arithmetic and precision, and then a decision problem is solved with cost these two functions when there exists a machine M satisfying the following. Given any input with finite condition number, so it's not ill-posed, the arithmetic cost, let me put it, the arithmetic cost on this input of the computation of m is bounded by the function arithmetic on the length and the precision. Furthermore, if the precision is bigger than this function on the size, then all computations of m correctly decide whether the input is in the set. So two remarks here. First, computations are clocked. That is, their arithmetic cost is bounded by a function on two parameters which are immediately available. I know the length of my input, and I know which is the precision that my machine is working at that time. Okay, so this is good. This is good. I know a priori how long will it take for the machine to stop. This is bad. Computations are unreliable. There is no guarantee that the precision used is enough to ensure a correct output. So even for exact computations, correctness is not guaranteed. Okay? But this is something that if I work with finite precision, I will have to learn to live with. I mean, there is no magical potion. Not even Harry Potter can solve that. Okay? Let me skip this. So let me now go to P. What will be P? I will call this P row, P with Roundoff. And I said that the decision problem belongs to Roundoff P, so Roundoff polynomial cost, when precision, the founded precision before, is bounded by a polynomial function. So if my precision is more than a certain polynomial, if my K mash is bigger than a certain polynomial in the size of my input, I am sure my answer will be good. And second, the function arithmetic in the length of ux and the precision of the size is bounded by a polynomial in the size. Okay? So when this happens, it means that, looking at the bit world, that you do a polynomial time bit computation and you get the right answer in the right time. Everything polynomial. There is a subclass that is interesting, which is the following. It's the same as before, but here I don't put K machine. So the time is always the same, independent on the precision. Let me give you a couple of examples. Assume I give you a matrix and they want to know whether the determinant is positive. Okay, you will compute the determinant. This will take you order of n cubed. Your matrix is n times n. And the time of doing the computation of the determinant, the number of arithmetic operations, will be independent on the precision you are using. Okay? Now, for some other algorithms, the time of computation somehow depends on the condition of your data, and then what you do essentially is you guess a certain condition and you set up the precision depending on the condition you guessed. Okay? Obviously, P direct is included in this P round-off.
And the inclusion is strict?
Yeah, the inclusion is strict.
Is this also obvious? Is this also obvious?
You can. No, it's not obvious, but it's easy. It's not obvious, but it's easy. Yeah, it is easy. So let me give you an example, very important example of problem in P direct. Take C, an algebraic circuit. N input gates, 1 output gate. And I consider the function from R to the N into R computed by the circuit. The circuit has arithmetic gates and some sort of sign gates, or sign gates, let's call it. Okay? And then I consider the subset of R to the N of the points that this function is greater or equal than 0. And let's say I want to decide whether, given a circuit C and a point X, fc of x is greater or equal than 0. Okay? So I am given C, I am given X, and I want to decide X belongs to a C. Okay? Now this is just the set, so to speak. I need to define the condition. In order to define the condition, I define rho eval of Cx, which is, well, if x is in SC, is the supremum over all epsilon, such that all epsilon evaluations is like epsilon computations. You do the evaluation of the circuit and you allow for errors, relative errors up to epsilon, just like the UMash before, okay? The same thing. All epsilon evaluations yield the good answer. And if it doesn't belong, all epsilon evaluations still yield the good answers. True already, okay. Then we take as condition number the following. 1 divided by this maximum. Non-deterministic, theorem, this is in PDR. Non-deterministic polynomial cost. Well, essentially, in these classical cases over the bits and over the reals, those are data for which we want to check whether we can check in polynomial time a proof. Okay, so data that have short proofs. Now, short here means small length, and here it's unclear what short proofs will be. One possibility is small length plus small condition. There is another which is asking small length plus small condition plus small magnitude. And this, if I had time, I would explain. Let me start with the class NPU, the unbounded. And then the idea is, a problem is here. Well, this is the definition. Essentially what I said is that if the data is in the set, then there exists a witness, a proof, in R to the m, where m is simply a polynomial in the length, such that this triple belongs to a set which is in P row, and the log of the condition number is bounded by a polynomial in the log of the condition number of ux. But you see, I have a set W, which is the one that will be in NP, and a set B, which is the one that will be in P. And what I said is that when I add my witness, the condition doesn't grow much. My condition on top. And if it's not in W, then no matter which y I take in R to the m, uxy is not in B, and the log of the condition is also smaller or equal than the log of the condition below. The log of the condition with the y is bounded with the log of the condition below. So all candidates of proof are short. One example would be circuit feasibility. Same input, just a circuit. But now what I want to know is whether there is a y such that y belongs to SC. Okay? And then what I do to define the condition number for this problem is I define a row feasibility of C, which is the supremum over all y's that belong of this row eval. If this set here, this condition here, is feasible, and if it's not feasible, I take the infimum. So in the feasible case, mu feas is the condition of the best condition solution, and in the infeasible case, it is the condition of the worst condition point in R to the m. Okay? Because this worst condition point is the one that, if I do a small perturbation, will become a solution. Okay? So proposition, this belongs here, and proposition P row is included in NP. There is a notion of reduction. I will skip it, but I will simply say that this notion of reduction satisfies the nice property, which is that if a problem W reduces to a problem S, and S is in P, then W is also in P. So one defines hardness and completeness in the usual way. A problem is hard in a class if all the problems in the class reduces to it. It is complete if in addition it belongs to the class. And then the theorem is that this problem is actually complete in this class. Okay? As a corollary, these two classes coincide if and only if we can solve this problem in P row. We don't know whether this is true, and we believe it isn't. Okay. Just to okay. Maybe we stop here.
Okay. Questions?
Does compactness play any role in your?
No. It's. I mean, well, in this NP, I didn't define it, but let me go here. As I mentioned, there are two. This NPB, your guesses in a way have small magnitude, means some sort of bounded condition. They will be in some bounded region. And then the funny thing is that I also have completeness here. I also have an NP complete problem here. And here I can prove that this is strictly included in exponential time. But this inclusion, this inclusion here, although I believe it is true, I couldn't prove it right now. And essentially it will boil down to take your algorithm, which is an infinite precision algorithm that solves this problem in the right amount of time, and do a fixed finite precision analysis of your algorithm. But this sounds scary. So I have somehow avoided doing it.
So maybe can you recall the differences between the B and the U version of the NP? So what is the...
I didn't, is that I skipped that. So I cannot recall it. I should have to explain it. And then Pascal will hate you.
Maybe it's a question. It's a question. Then
You're allowed to show it now, but it's a question.
what is the difference between the B and the U in the definition?
So essentially,
Should be paying attention to the timer.
Ah, okay.
Maybe the next
Then
slide
I
will
ask
start.
it afterwards.
yeah.
All right. Take it offline. Okay. Well, okay, thanks.